So our goal for this section is being able to find sample spaces and then also be able to find experimental and theoretical probability. So let's go through some definitions first. So this may be something, I'll read through them, but this may be something you want to pause and write down the definitions. So the first one says that the probability, a probability experiment is an action or a trial that has varying results. Outcomes are the possible results of a probability experiment. Events, a collection of one or more outcomes, and sample space is the set of all possible outcomes. Now, these aren't going to make a lot of sense until we go through and talk about them, but if you want to stop and write down those definitions, you can. All right, so here's an example. It says you flip a coin and roll a six-sided die. How many possible outcomes are there in the sample space? So list the possible outcomes. So let's list the possible outcomes. One thing that can help you with this to make sure you don't miss one is you can do a tree diagram. So we're going to flip a coin. So if I flip the coin, I could get a heads or I could get a tails. Now I could get a heads with the coin and then I roll a six-sided dice. When I roll the six-sided dice, I could get a 1, 2, 3, 4, 5, or 6. Or I could get a tails and get a 1, 2, 3, 4, 5, or a 6. So if you think of all the outcomes here, it could be a heads 1, heads 2, heads 3, heads 4, heads 5, or heads 6. Or it could be a tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. Okay, so if you count them up, how many possible outcomes are there? Total of 12, right? They've got 6 there and 6 there. So there are 12 possible outcomes, and here's a list of all those. Now this actual list, this right here is what we say is a sample space. So a sample space is really just a list of all the possible outcomes that you could come up with. So the sample space for this problem is right there. Okay, so it says find the number of possible outcomes in the sample space, and then list the possible outcomes. Okay, so if I flip 2 coins, all right, so if I flip 2 coins, I flip the first coin, it could be a heads or a tail, and then I flip my second coin, it could be a heads with the first and a heads with the second, or a heads with the first and a tails with the second, or it could be a tails heads and then or a tails tails. So my my sample space looks like this. It could be a heads heads, heads tails, tails heads, or tails tails. So this right here is my sample space. Now the question itself says find the possible number of outcomes in the sample space. Well, there's a total of 4 there, right? You can really just count here at the bottom, 1, 2, 3, 4 across there, and that will tell you how many possible outcomes there are. Okay, so you flip 2 coins and you roll a 6-sided dice. All right. Well, just think about this for a second. I'm not going to write out the whole sample space, but we just flipped 2 coins up here. Now for each of these, right, I could do a heads, heads, and then I could have a 1, 2, 3, 4, 5, or 6. Or I could do a heads, tails, and have 6. Or I could do a tail. So if you count, there's going to be 6 outcomes here. There'll be heads, tails. There'll be 6 more down here. There's 12. Tails, heads, 6 more. There's 18. Tails, tails, and 6 more. So there's 24. So you can kind of figure that out doing that tree diagram without having to write out the entire sample space. But that's how we would do it. Oops, sorry about that. All right, if you look at this next example, or next information, it says the probability of an event. All right, that's what we're going to spend the next chapter is dealing with probabilities, this whole unit. So it says the probability of an event is the measure of the likelihood or the chance that an event will occur. Probability is a number from 0 to 1, okay, including 0 and 1, and can be expressed as a decimal fraction or a percent. So see if this makes sense, right? If something has a probability of 0, that means that it is impossible. It can't happen. And you could write it as 0. The decimal would still be 0%. Over here, if the probability is 1, that means it's going to happen. Like there's no other choice. Again, or 100%. Right here in the middle, we have probability of 1 out of 2. That'd be the same as 0.5 or 50%. So you can write it as a fraction, decimal, or as a percent. Probably the most common one, honestly, is a decimal. You'll see that a lot. If it's got a 1 in 4 chance, that's pretty unlikely, right? 3 in 4 chance, that's pretty likely. So we have this spectrum, but it can't be less than 0, can't be greater than 1. Here's, right, 0 would be, I don't know, pigs fly. 1 would be, right, impossible to happen. 1 would be, you're watching this video. Well, that's certain because you are watching the video right now. So when you go to find, there's two different types of probability. The first one is what we call theoretical probability. So theoretical probability you find without actually doing anything. You're just thinking about how, the number of outcomes and the favorable outcomes and how it works, but you're not actually performing the event. So what you do is you take the number of favorable outcomes over the total number of outcomes. The way we write that, the probability of event A is written as, we just take probability of A. That's how you write that. Okay, so that means this. The probability of event A, that means the same thing. Let's find some probabilities. So it says a student taking a quiz randomly guesses on the answers to 4 true and false questions. What's the probability the student guesses exactly 2 correct answers? So to do this, we need to figure out 2 things, right? I need to figure out the number of favorable outcomes and the number of total outcomes. So let's see if we can do that. Probably the easiest way to do here in this one is we just write out the sample space. So I take the first question, right, and I could get a true or a false. And then if I got a true on the first one, I could get a true on the second one or a false on the second one. Same thing here. There's all the results to 2 questions. We have to do 4 of them, right? True, false, true, false. True, false. There's 3 questions. The 4th question, true, false, true, false. Running out of room here. I'm just going to squeeze it in there. True, false, true. Okay, so we want to find out, first of all, right, the bottom of the fraction, I want to find the probability. Let's call this event up here. The probability says, what's the probability of the student guessing exactly 2 correct answers? So we'll call that event A as getting 2 correct answers. So what is the probability of A? So it's the number of favorable outcomes over the total number of outcomes. For the total number of outcomes, we just count at the very bottom of our tree here. So, right, we could have a true, 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 or true, 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 false. But in the end, I'm just counting how many of these. So there's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's a total of 16 outcomes. 16 different ways you could answer those 4 questions, combinations of those 4 questions. Okay, now I need to figure out how many favorable outcomes. So to be a favorable outcome, right, if we're reading up here, is that I get exactly 2 correct answers. So how many of these have exactly 2 correct answers? This one has 4. This one has 2, 3. This one has 2. That one would be exactly 2. If I trace this one down here, that would be exactly 2 correct answers. There's 1. Let's see if we can find another one. Got true, false, true, true. That would be 3. True, false, true, false. That one would work. There's exactly 2 favorable outcomes. Let's see what else. So I got true, false, false, true. That would be 2 outcomes. Come over to this one. There's 3. I got false, true, true, true. That one would work. False, true, true, false. So that one right there. False, true, false, true. That would be 1. I got false, false, true, true. That one would work. Then I've got false, false, true, false, no, false, 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 true, false, 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 true, false. So that one wouldn't work either. Okay, so let's count them up. I got 1, 2, 3, 4, 5, 6. Total of 6. I'm going to come over here. That's how many favorable outcomes I had. Okay, so we could reduce that, right? 6 over 16, divisible by 2 would be 3 out of 3/8. That's one way to write the answer, and that's fine. If you want to go 3 divided by 8, it comes out to be 0.375. So you could write that same answer as 0.375. Or if you want to, you could even write it as a percent, 37.5%. So looking at that now, that's one way to look at it. If you wanted to, we could have made a list of the actual sample space, and I could have gone true, 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 and just started listing it out. True, 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 false, and basically just follow this tree down and keep listing it until I have them all done. True, true, false, true, and then list the actual sample space out. We would have got 16 different ones and found out. So that's another way to look at it too, is by actually listing the sample space. It could be a bit time consuming. I kind of like just looking at the tree diagram. Sometimes it's easy to miss one there. Hopefully I didn't, but that can sometimes happen. So you just got to be careful with that. All right, so here's just a little more definitions here for you. It says the sum of probabilities of all outcomes in a sample space is 1. What that's basically saying is if I find the sum of all the probabilities, what's the probability of getting exactly 2 correct answers, or what's the probability of getting something else? If I add those all up, it has to add up to be 1 because, all the answers have to be included in there. This one says the sum of the probability of all outcomes in a sample space is 1. So when you know the probability of event A, you can find the probability of its complement. Okay, the complement of an event consists of all the outcomes that are not in A. Okay, so if you want to underline or write that down, the complement of an event A consists of all the outcomes that are not in A. And the way you do that symbol is just that A with the line over it. Okay, and you could say A bar is the way you'd say that. I think you just say the complement of A would be great. So basically the complement is, here's an example. What's the probability that someone makes their foul shot? Well, the complement of that would be the probability of someone missing their foul shot. Or you could have a deck of cards. What's the probability of drawing an ace? The complement of that would be the probability of not drawing an ace. So it's basically the probability of an event is all the way the event can't occur. So if probability of drawing an ace, there's a deck of cards, there's 4 aces. Well, all the others are not aces. So all the others represent the complement of drawing an ace. So this is what we just read there, right? The probability of a complement of an event is, so the probability of this complement is just 1 minus the probability. So what it's basically saying is, let's say that event A, event A is, it's going to rain today. And let's say we know the probability of A, probability of it raining, watch the weather or whatever, it says there's a 37% chance or 0.37% chance. So what would be the probability of the complement? Well, the complement, right, A primed, is the probability that it doesn't rain today. Well, what this says up here is if I go 1 minus, let me fix that. What it's saying up here is if I go 1 minus 0.37, that will give me the probability of its complement. So 1 minus 0.31, 37% chance it rains, you subtract those, you end up with, what's that? It's 0.63. So does that make sense? If there's a 37% chance it's going to rain today, there's a 63% chance that it's not going to rain today. Okay? So not raining would be the complement of raining. So if you always take 1 minus the probability of something happening, it will always tell you the complement of that happening. So here's some examples. The first one says, you roll a 2-sided dice. Let's find the probability of each event. The first one says the sum is not 6. So there's 2 ways you could do this. One is, I could find the probability that the sum is 6. That's a little easier to count. Let's find all the ones that sum is 6. There's 2, 3, 4, 5. That one right there would be 6. That'd be 7. That one right there would be 6. That would be 7. That would be 5. That one right there would be 6. That's going to be less than 6. Those are going to be bigger than 6. There's 6. And there's, I think that's it. Those are the only ones that add up to be 6. So how many are there? 1, 2, 3, 4, 5. So probability of the sum is a 6 is 5 out of, and how many possible outcomes? This is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So out of 36. So the probability of the sum of 6 is 5 out of 36. But the question was, what's the probability that the sum is not 6? Or the complement of that? Well, all I have to do is go 1 minus 5 over 36. So that'd be 36 over 36 minus 5 over 36. 36 minus 5 is 31. So we can use, knowing this probability, we can find the probability of its complement by going 1 minus that. I'll look at this next example. So it says, let's see, the sum is less than or equal to 9. Okay, so the sum is less than or equal to 9. Now we could do this two ways. I could just count up how many sums are less than or equal to 9. Or I could add up how many sums are greater than 9. We could do it either way. So like all the way through here, that's 2, 3, 4, 5, 6, 7. Those are all less than or equal to 9. This is 8, so those are all less than or equal to 9. Now this one right here is equal to 9, so it's still good. This one's equal to 10. That one's equal to 9. That one's equal to 9. And that one's equal to 9. So I think it's just all these. I got 1, 2, 3, 4, 5, 6. So there are 6 out of, so the probability the sum is less than or equal to 9 is equal to, let's see, 1, 2, let's see, there are, 6 that are greater than 9? So there are 30 that are less than or equal to 9. So by knowing knowing the complement, knowing that there are 6 of them, I know that there has to be 30 of them that are not. So 30 out of 36, which you could write as divided by 6, you could write that as being 5, 6. Or again, if you want to write it as a decimal or a percent, you could do that also. So sometimes it's easier to find the probability of the complement and then to subtract it from 1 to find the probability of an event happening. All right, this says you flip a coin and roll a 6-sided dice. What's the probability that the coin shows tails and the dice shows 4? So let's see if we can figure this one out. This really doesn't have anything to do with a complement. Let's just write our sample space out. So we did this up above, but you could get a heads and a 1, a heads and a 2, a heads and a 3, heads and a 4, heads 5, heads 6, or tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. So what's the probability the coin shows tails and the die shows 4? Well, how many of those are in there? Let's see. A tails 4, there's only one, right there. So that would be 1 out of, let's call this event A over here. I don't want to write it all out. So the probability of A happening, which is coin shows tails and dice shows 4, would just be 1 out of 12. And there's 12 possible outcomes. Only one of them has a tails and a 4. Okay, if you look at this one, what's the probability that of the complement of A? Well, it tells me the probability of A. So to find the probability of the complement of A, I just go 1 minus 0.45. So what's that? 0.55. Again, probability of the complement would be 1 minus 1/4, 3/4. Okay, if the probability of A happening is 1, just think about this. What would be the probability of the complement of A? Well, if something's going to happen, then its complement can't happen, right? Probability of equal to 0. Probability of the complement of A is equal to 1 minus 0.03. Okay, so if you know the probability of an event happening, you can find the probability of the complement of that event happening. Hey, experiment. So what we've been doing is theoretical probability. Experimental probability is different. It's based on repeated trials of a probability experiment. So instead of saying, hey, a dice has 6 sides, what's the probability of getting an even? Well, it'd be 3 out of 6, right? 3 evens out of 6 possible outcomes. With experimental, it's different. with experimental, you actually take a dice and you roll it over and over and over and over and over again. You count the number. You count how many times you get an even out of the total number of times you rolled it. So experimental probability you find by doing. So if that makes sense. You find, so experimental probability is based off of repeated trials. If you want to put underneath there, it's by doing the experiment. You're doing the experiment and you're gathering the data. And all you do is take the number of successful outcomes in your experiment over the number of trials in your experiment. All right, so this says each section of a spinner shown has the same area. The spinner is spun 20 times. The table shows the results, so they counted how many times you got each one. For which color is the experimental probability stopping on the color the same as the theoretical probability? Okay, so let's figure out the experimental probability. So over here is our table, right? They just spun it a bunch of times and found what they got. So if they spun it 20 times, for the red one, they got it 5 out of 20 times, which we could reduce that. What's that, 1/4? For the green, they got 9 out of 20 times. For the blue one, they got 3 out of 20 times. And for the yellow one, they got 3 out of 20 times. So that's the experimental probability. So if I said, what's the experimental probability of getting a red? You'd say, hey, it's a 5 in 20 or a 1 in 4 probability of getting that. You know, what's the experimental probability of getting a green? Well, it's a 9 in 20 chance. So the question was, for which color is the experimental probability of stopping on the color the same as the theoretical? So let's do that. If these 4 have the same area, they're equally likely to get chosen. So to get a blue would just be a 1 in 4 chance. To get a yellow, 1 in 4. To get a red, 1 in 4. To get a green, 1 in 4. So which one does the experimental match with the theoretical? That'd be this one right here. Like the probability of getting a red was both 1 in 4, both using theoretical, right? There's 4 equal areas, and 1 out of those 4 was red. And basing this, you have the same. So again, theoretical is based off of the number of possible outcomes, number of favorable outcomes, but you don't actually do the experiment. Experimental, you actually do it and see what happens. For which color is the experimental probability of stopping on the color greater than the theoretical probability? This is the same questions up above. We can look back up here and see what we got. Let's see. Is it 9 out of 20 greater than 1/4? So it would be the green. The blue and the yellow, the theoretical came out to be a smaller probability than the actual, right? 3/20 is less than 1/4 on that one. Hey, last thing you need to know. Oh, let's actually do this one. This is a good one. It says, in the United States, a survey of 2,184 adults ages 18 and over found that 1,328 of them have at least one pet. The types of pets these adults have are shown in the figures. What is the probability that a pet-owning adult chosen at random has a dog? Okay, so here's all U.S. adults with pets. How many of them had dogs? Well, there are a total of 916 that had a dog. Those are the 916. Those are the favorable outcomes out of the total, which was 1,328. So one thing just to be careful with, I did say what's the probability of a pet-owning adult chosen at random has a dog. So I'm not looking at all the people. I'm only looking at the pet-owning adult. That's why it was only out of the 1,028, because those are the ones that had at least one pet. And out of those, 916 had a dog. And again, you could write that as a reduced fraction. You could change it to a decimal or a percent, however you want to look at that. So you were in a, what's the probability of pet-owning adult chosen at random owns a fish? That would just be 146 out of that same number, which was 1,328. Hey, here's the last thing you have to know, odds. So odds is a little different than probability. The odds of an event compare the number of favorable outcomes to the unfavorable outcomes. So that's different. With probability, you compare the number of favorable outcomes to the number of possible outcomes, the total number of possible outcomes. With odds, you compare the favorable to the unfavorable. Okay, so odds in favor, favorable to the unfavorable, or odds against the unfavorable to the favorable. So it says find the odds that the odds in favor of stopping on a yellow. So how many yellows are there? There's 1, Usually with odds, you write it this way: 1 dot dot, and then how many are not yellow. So the odds in favor, right? That's in favor, 1 yellow. There are a total of 3 others, so it's 1 to 3. Now, if I asked you for the probability of getting yellow, that'd be 1 out of the total number of outcomes you would count the yellow, right? 1 out of 4. So the difference is, right? Probability, this is out of the total, okay? Whereas this number is the unfavorable instead of the total. So it's a little bit different than probability. Okay, the probability of winning a balloon dart game is 0.2. The odds of winning a ring toss game are 1 to 5. Which game gives you a better chance of winning? So it's a little tricky because this first one's a probability is 0.2. Let's write 0.2 as a fraction. Remember, 0.2 is the same as 2 out of 10, which is really 1/5. So you have a 1 in 5 chance of winning a balloon dart game. Now the odds of winning a ring toss are 1 to 5. Now this is different. If there's 1 favorable outcome and there's 5 unfavorable outcomes, that means there's a total. You have 1 favorable outcome compared to the number of total outcomes. You have to add those together. The favorable outcome 1, unfavorable 5, there's a total of 6. So if you convert the odds over to probability, you just have to add those two together. That gives you the total number of outcomes. So I have a 1 in 5 chance of winning the balloon dart. I have a 1 in 6 chance of winning the ring toss. This one is, this is which one gives you a better chance of winning? It would be the balloon dart right there. So you can convert odds over to probability when you're comparing those. I think that's about it. Exam, yeah, I don't think we need to go back and do that. So I think that's about it. Big things here. Make sure you know what theoretical probability is, right? That's when you calculate it without doing anything. You're just looking at kind of the theory behind it, how many favorable outcomes, the number of possible outcomes. Whereas experimental, you're actually doing it, actually performing the experiment and recording results, and you use that to find your probability. And then just remember, odds are different. You're comparing favorable to unfavorable instead of favorable outcomes to total. Okay, that's a big difference there. All right, good luck.